Our future home may not be a single world, but a network of 20 celestial outposts. This is the new reality emerging from the icy crusts and thin atmospheres of moons in our own solar system. By the end of this exploration, you will see our cosmic neighborhood not as a handful of planets, but as a vast archipelago of possible new homes. What does it take to build a city on a moon with a subsurface ocean, or a station floating on a lake of liquid methane? The answers will redefine what it means to be a multi-world species. Are you ready to see which of these distant worlds could be our next address? That traditional image of a habitable world, basking in the warm glow of a star, is incomplete. For decades, we searched for planets in the Goldilocks zone, a narrow band around a sun where liquid water could exist. But this star-centered view of habitability has blinded us to a much richer reality. Our solar system is teaching us a new lesson, that life, or at least a human presence, can be sustained far from a star's warmth. The key lies in a concept called niche habitability. Instead of a planet being warmed from the outside by a sun, imagine a world warmed from the inside. This internal heat can come from the relentless gravitational tug of a giant planet, creating tidal forces that flex and heat a moon's core. It can come from the decay of radioactive elements deep within a rocky body, providing geothermal energy, or it can come from chemical reactions between rock and water, releasing energy that could power simple ecosystems or human machinery. This paradigm shift is monumental. It transforms dozens of distant, frozen moons from barren rocks into potential oases. Think of it not as a single garden world, but as a cosmic archipelago. Each island in this chain, each moon, possesses a unique environment. One might have a global ocean sealed under an icy shell, heated by tides. Another might have lakes of liquid methane on its surface, requiring entirely different technology to harness. A third could have vast deposits of water ice right on the surface, ready to be mined. Surviving on each of these islands will demand a tailored strategy, a specific set of tools and habitats designed for that world's particular mix of resources and dangers. This foundational idea reframes our entire quest. We are no longer just looking for a second Earth. We are scouting for a network of specialized outposts, each playing a role in a larger, interplanetary civilization. The search is no longer for a single home, but for a neighborhood. A cracked, pale marble hangs against the vast darkness, its surface etched with a labyrinth of reddish-brown scars. This is Europa, and its fractured face is the first clue to a secret held within. Beneath that shell of ice, perhaps 10 to 15 miles thick, churns a global ocean of liquid salt water. The staggering truth is this single moon holds more liquid water than all of Earth's oceans combined. It is not the sun that keeps this distant sea from freezing, but the immense gravitational embrace of its parent planet, Jupiter. As Europa orbits, Jupiter's pull stretches and flexes the moon's core, generating immense tidal heat. This internal furnace is so powerful it prevents the entire subsurface ocean from turning to solid ice, maintaining it as a dark, watery realm. For scientists, this makes Europa one of the most compelling places in our solar system to search for signs of life beyond Earth. The upcoming Europa Clipper mission, set to arrive in the 2030s, will conduct detailed reconnaissance, mapping the ice shell and probing the ocean's depth and salinity from orbit. Its goal is to understand if this hidden world has the necessary ingredients and energy to support biology. For future settlers, however, Europa presents a profound duality of promise and peril. The promise is that vast, accessible water, a fundamental resource for life support and rocket fuel. The peril is everything else. Establishing a human outpost here means solving the puzzle of the ice. How do you access that ocean? One concept involves robotic melt probes called cryobots, using heated drill heads to slowly descend through the frozen crust, potentially taking months to reach the liquid water below. Once through, submersible explorers could search for hydrothermal vent systems on the ocean floor, where mineral-rich water, heated by the moon's core, might create chemical oases. These could be the very places where alien microbial life, if it exists, has thrived for eons. Yet the surface is a deadly place. Europa orbits within Jupiter's ferocious radiation belts, bathing the landscape in particles that would be quickly fatal to an unprotected human. Any surface station would need to be buried deep within the ice for shielding, or visits would be strictly robotic and brief. This leads to a fascinating and deeply respectful question for the future. What if, after we build a research base and finally send probes into the abyss, we discover we are not alone in that ocean? Establishing a human presence on Europa would then become an act of profound responsibility, shifting from mere exploration to careful stewardship, ensuring our search for knowledge does not disturb a separate, ancient story unfolding in the dark. While Europa's ocean remains locked beneath a frozen vault, another moon offers its secrets freely into the void. Enceladus, a small, brilliant world orbiting Saturn, performs a spectacle of cosmic generosity. From fractures near its south pole, towering geysers blast water ice, vapor, and organic molecules hundreds of miles into space. The Cassini spacecraft did not just photograph this phenomenon, it flew directly through these plumes, tasting their contents. What it found was nothing short of revolutionary. The spray contained not just water, but the basic chemical ingredients for life, including methane, carbon dioxide, and ammonia, alongside a critical source of chemical energy. This discovery transformed Enceladus from a quiet ice ball into one of the most promising places to search for life in our solar system. For a future outpost, the implications are staggering. Here, you would not need a complex drill to reach the subsurface ocean. The ocean is, in a very real sense, coming to you. These continuous eruptions provide a direct sample of the hidden sea, a ready-made resource stream of water and potential fuel. Imagine a robotic spacecraft, a plume diver, designed not to land but to repeatedly swoop through these icy jets, collecting fresh material for analysis. Or picture a surface station anchored near the tiger stripe fractures, equipped with collectors that gather the falling ice, melt it for water, and process its chemicals. This turns a distant moon into a convenient filling station and a front-line laboratory. The energy source driving these plumes is the same tidal heating we see at Europa, but here it is so intense it cracks the icy shell open, creating a natural pipeline. This makes Enceladus uniquely accessible. Any mission here would have a dual purpose, searching for signs of biological activity while simultaneously harvesting the very resources needed to sustain human presence and propel missions deeper into the Saturnian system or beyond. The question it poses is profound and humbling. If we find even the simplest forms of life in those ejected ice grains, it would suggest life is a common phenomenon in the cosmos, arising wherever the right conditions persist. Building an outpost on Enceladus would then become an act of incredible care, a commitment to study and protect a potentially living world while using its non-living resources to expand our reach. It presents a model for how humanity might responsibly interact with other ocean worlds, learning from them without causing harm. But the most alien paradise in our solar system orbits that same ringed giant. Titan is a world draped in perpetual orange twilight, where the very rules of chemistry are rewritten by the cold. Here, at 290 degrees below zero, water is harder than granite, and the rocky landscape is carved not by rivers of water, but by flowing liquid methane and ethane. Vast lakes of these hydrocarbons dot the polar regions, and gentle rains of methane fall from thick, hazy clouds. What makes Titan truly unique, however, is its air. It is the only moon in our solar system with a substantial atmosphere, a dense blanket of nitrogen that is actually thicker than Earth's own. This is a game-changer for human exploration. That thick atmosphere provides a natural shield against cosmic radiation, something every other moon on our list desperately lacks. More astonishingly, it means flight is easy. The combination of low gravity and thick air means a human wearing a wingsuit could simply run and take off. Robotic aircraft or simple rotor drones could survey this strange landscape with an efficiency impossible on airless worlds. The resources are just as revolutionary. Titan's atmosphere and surface are saturated with organic, carbon-based compounds. Think of it as a pre-industrial chemical refinery, offering the basic building blocks for plastics, synthetic rubbers, and fuels. You would not need to bring complex manufacturing materials from Earth. You could literally grow them from the atmosphere. The challenge, of course, is the profound, soul-crushing cold. Machinery designed for Earth or even Mars would become brittle and fail. Heating any habitat would require constant, significant energy. Yet, the solutions might lie in Titan itself. One tantalizing concept involves using the moon's own chemistry for power. By combining the abundant methane with oxygen split from water ice, which is plentiful in Titan's crust, you could create combustion or fuel cell systems, turning the moon's lakes into literal power stations. This paints a picture of a future outpost unlike any other. It would not be a buried bunker in ice or a dome on a desert. It could be a collection of insulated habitats perched near a methane sea, with aircraft flitting between them, harvesting atmospheric gases and using local chemistry to build and power a settlement. Titan represents more than an outpost. It is a testbed for a completely novel branch of human civilization, one that learns to thrive not by replicating Earth, but by mastering an environment that follows its own deeply alien rules. While Titan redefines the chemistry of survival, another moon offers a far more classical, yet equally critical form of sanctuary. Callisto presents a landscape of profound stillness, its face marked by countless craters, a record of impact spanning billions of years. This ancient, battered surface of dark rock and bright ice holds a secret of immense strategic value for humanity's future. Unlike its dramatic siblings Io, Europa, and Ganymede, Callisto orbits at a respectful distance from Jupiter, placing it safely outside the planet's most ferocious radiation belt. This single fact transforms it from a mere moon into the solar system's most promising gateway. For the first time, we are looking at a world in the outer solar system where humans could potentially work on the surface without being immediately condemned by an invisible, lethal storm. This changes everything for operating in the Jovian system. Imagine a primary outpost established on Callisto, a fortified hub of activity. From this relatively safe vantage point, teams of engineers and scientists could pilot sophisticated robotic avatars on the far more dangerous surfaces of Europa and Ganymede in real time, with only a fraction of a second delay. They could drill into Europa's ice, navigate Ganymede's complex terrain, or maintain intricate scientific instruments, all while their physical bodies remain shielded within habitats built from Callisto's own resources. That is the second key advantage. The moon itself provides the building materials for its own fortifications. Callisto's surface is rich in water ice. This ice is not just for life support, it is the perfect radiation shield. By piling up regolith, the moon's soil, or by using processed water to create thick ice walls, settlers could construct habitats that offer robust protection from cosmic rays and solar storms, turning a surface base into a secure underground complex. Furthermore, spectral data suggests Callisto, too, may harbor a subsurface saltwater ocean, though deeper and under more pressure than Europa's. This potential reservoir adds to its long-term resource portfolio. Strategically, this makes Callisto the ideal staging ground, a cosmic port of call. Inbound spacecraft from the inner solar system could use its gravity to slow down and refuel, processing local water into hydrogen and oxygen propellant. Outbound missions to the Saturnian system or beyond could resupply here. It becomes the first durable foothold, a place where infrastructure is built to last, enabling the careful, sustained exploration of its more volatile and biologically fascinating neighbors. Callisto may not have the dramatic plumes of Enceladus or the methane lakes of Triton, but it offers something arguably more precious for a fledgling interplanetary civilization, a stable and defensible home base from which to conduct the most sensitive operations across an entire planetary kingdom. Ganymede is a world that does not simply exist in space, it defines its own. As the largest moon in our entire solar system, it is actually bigger than the planet Mercury. But its most remarkable feature is invisible, a protective force field generated from within. Ganymede is the only moon known to possess its own intrinsic magnetic field, a rare and precious bubble of safety in the Jovian system. While it cannot fully deflect the onslaught of Jupiter's radiation, it creates pockets of relative calm, zones where radiation levels are significantly lower than on its unprotected neighbors like Europa. This magnetic shield makes Ganymede's surface a more plausible place for long-term human activity, a place where surface structures might endure with less shielding than would be required elsewhere. The grandeur continues beneath the crust. Ganymede's interior is a complex layer cake of worlds within a world. At its heart lies a metallic core, likely rich in iron, which is the dynamo generating that protective magnetic field. Surrounding that is a rocky mantle, and above that lies its crown jewel, a colossal subsurface ocean. Current models suggest this ocean is not simply resting on rock, but is instead sandwiched between distinct layers of ice, a vast, dark sea trapped between a ceiling and a floor of frozen water. This leads to a fascinating concept for astrobiologists, the idea of a habitable layer. Somewhere within that immense icy shell, where internal heat from the core meets the right pressure and mineral seepage from the rocky mantle below, there could be zones where liquid water pockets persist, warmed by the moon's own geothermal heart. These could be stable environments, isolated for eons, where the basic ingredients for life might have found a way to combine. For future settlers, the scale of everything on Ganymede is both the ultimate promise and the primary challenge. Its resources are titanic, with more water ice than you could ever use. Yet, that very size comes with a physical consequence we rarely consider on smaller moons: noticeable gravity. Ganymede's gravity, while only about 1/7 of Earth's, is still substantial. This means landing a heavy spacecraft requires more fuel and precision than on a tiny asteroid. Conversely, launching back into space from its surface demands a real rocket, not just a gentle hop. It is a world that commands respect through sheer physical presence. Establishing an outpost here would be an exercise in managing scale, harnessing the moon's massive resources and unique magnetic protection to build what could become the capital city of the Jovian frontier, a bustling hub overseeing operations across an entire miniature solar system of its own. Far beyond the familiar giants, in the silent, sun-distant reaches of our solar system, lies a kingdom of profound and elegant strangeness. The Uranian system is a place of deep freeze and perpetual twilight, its axis tilted so dramatically that the planet and its moons essentially roll around the sun on their sides. Orbiting this pale, blue-green ice giant are 5 major moons, each a frozen sentinel holding clues to a tumultuous past. Miranda, Ariel, Umbriel, Titania, and Oberon are not merely points of light. They are a complete geological laboratory, a diverse collection of icy worlds that could one day serve as stepping stones into the outermost dark. Their surfaces tell stories of shattering impacts, internal warmth, and ancient stillness, offering a masterclass in how celestial bodies evolve in the deep cold. For future explorers, this system presents a unique opportunity, a single destination where you can study 5 different chapters of solar system history and potentially tap into 5 distinct sets of resources, all within the gravitational domain of one planet. The most immediately striking of these worlds is Miranda. Seen up close, it looks less like a coherent moon and more like a celestial patchwork quilt, a jumble of bizarre, mismatched terrains violently stitched together. Vast chevron-shaped grooves and towering cliffs 20 kilometers high scar its face, features that suggest a history of almost unimaginable violence. The leading theory is that Miranda was shattered by a colossal impact in the distant past, its pieces drifting apart before slowly, painfully, reassembling under their own gravity. This makes Miranda a frozen monument to cosmic destruction and rebirth. For resource prospectors, such a fractured world could be a treasure trove, as cataclysmic events likely brought deep, mineral-rich material from its core up to the very surface, making it accessible without complex drilling. It is a world where the very process of its near death may have created the easiest path to the resources needed for new life. In stark contrast to Miranda's chaotic visage, Ariel presents a smoother, younger countenance. Its surface is cross-cut by an extensive network of valleys and fault lines, clear evidence that this moon was once geologically active. Something warmed its interior long ago, perhaps the tug of Uranus's gravity or the decay of radioactive elements, causing its icy crust to stretch and crack. This past activity suggests Ariel may have reservoirs of relatively pure water ice closer to the surface, deposited by ancient flows or upwellings. A base here could focus on harvesting this cleaner ice for life support and fuel, while studying the tectonic patterns to understand how even small, frozen worlds can harbor dynamic hearts. The narrative shifts again with Umbriel and Oberon, the ancient historians of the system. Their surfaces are dark, heavily cratered, and seemingly unchanged for billions of years. They are cosmic archives, their faces preserving the record of the early solar system's violent bombardment. Umbriel, in particular, is one of the darkest major moons, its surface likely coated in a layer of dark, organic material or radiation-processed ice. This very darkness could be a resource, as complex carbon compounds are the building blocks for plastics and other synthetic materials. Oberon, the outermost of the 5, shares this ancient, battered character, with large mountains that may be the remnants of a gigantic impact. These 2 moons offer stability and a wealth of primordial material, perfect locations for long-term observational outposts or mining operations focused on carbon and other ancient volatiles frozen in time. The crown jewel of the system, however, is Titania. As the largest Uranian moon, it commands attention not just by size but by feature. A massive canyon system scars its surface, a rift valley that could be evidence of global expansion in its past. This hints at a history of internal activity, and like its larger cousins around Jupiter and Saturn, Titania is a prime candidate for a subsurface ocean. A layer of liquid water kept fluid by a mix of internal heat and antifreeze salts like ammonia could still exist today, sealed beneath an icy shell. This possibility elevates Titania from a mere resource depot to a world of profound scientific priority. An outpost here would have a dual mission, mining the abundant surface ice for practical needs while deploying sensitive seismometers to listen for the subtle slosh of a hidden sea, searching for echoes of liquid in the eternal freeze. Together, these 5 moons present a compact portfolio of deep space opportunity. They offer a range of geological histories, from the reassembled rubble of Miranda to the potentially active ocean world of Titania, and a spectrum of resources from pure water ice to dark organic compounds. Establishing a human presence in the Uranian system would mean learning to operate in the most extreme, sun-deprived cold we have yet encountered, pushing our technology and our resilience to their absolute limits. It would be the ultimate test before venturing to the final, lonely frontier, the realm of the solar system's most distant giant, Neptune, and its enigmatic, tempestuous moon. Yet beyond even the tilted realm of Uranus lies a kingdom of profound and lonely grandeur, the final outpost of the solar system's great giants. Here, orbiting a deep blue world of supersonic winds and eternal cold, we find a moon that defies every expectation. Triton moves in reverse, a celestial rebel circling Neptune backwards against the planet's own rotation. This single, glaring clue reveals a breathtaking history that Triton is not a native of this system, but a captured wanderer from the distant Kuiper belt, a primordial world dragged into captivity by Neptune's immense gravity. Its surface is a study in alien geology, a landscape of frozen nitrogen, water ice, and exotic ices like methane and carbon monoxide, forming a crust that resembles a cracked, pinkish cantaloupe. But this is no dead world. Voyager 2 observed active geysers erupting from its surface, dark plumes of nitrogen gas and dust shooting kilometers into its thin atmosphere, driven by the faint, distant warmth of the sun as it triggers seasonal sublimation beneath the ice. This activity suggests a dynamic, if subtle, interior, a place where change still occurs even at the very edge of light. For a future outpost, Triton's captured origin is its greatest gift. As a former Kuiper belt object, its composition is a frozen time capsule from the solar system's earliest days, likely rich in volatile compounds like ammonia and methane. These ices are more than scientific curiosities. They are the raw materials for life support, fertilizer production, and advanced propulsion systems. Harvesting the nitrogen ice alone could provide both a breathable buffer gas for habitats and a crucial component for industrial processes. A base on Triton would be a gateway to the outermost dark, a fueling station and laboratory perched on the solar system's final ledge. In stark contrast to Triton's complex story, its neighbor Proteus presents a simpler, more rugged proposition. Neptune's second largest moon is a dark, irregular lump, a world not large enough for gravity to pull it into a sphere. It is a testament to utility over beauty, a celestial rock that could serve as an ideal resource depot. Its dark surface likely contains carbon-rich material, and its low gravity would make landing and lifting cargo exceptionally efficient. A robotic mining station on Proteus could process local regolith into radiation shielding or harvest water ice for shipment to a larger base on Triton, creating a local, two-world economy. Establishing a human presence this far from the sun represents the ultimate test of endurance and independence. Solar power here is 1,000 times weaker than at Earth, a faint, useless glimmer. Survival would depend almost entirely on nuclear fission or advanced radioisotope systems, providing the constant, dense energy needed for heat, light, and industry. Every system would need to be closed-loop, recycling every drop of water and every molecule of air with near-perfect efficiency. A journey to this outpost would be a one-way trip lasting over a decade with current technology, meaning the first settlers would truly be leaving Earth behind, committing to a life in the permanent twilight of the solar system's frontier. To live on Triton would be to live in humanity's most remote lighthouse, its beacon turned not toward the sea, but toward the infinite black of interstellar space. But before we commit to voyages lasting decades into the outer dark, there is a closer, more immediate classroom. Orbiting the rust-colored deserts of Mars are two strange, lumpy sentinels, Phobos and Deimos. These are not worlds in the traditional sense, but captured asteroids, dark and potato-shaped, each no larger than a modest city. Their modest scale, however, is the source of their immense strategic value. They are not destinations for grand colonies, but the solar system's most perfect stepping stones, rich in carbonaceous material and potentially holding water ice within their dusty regolith. These moons are essentially pre-positioned resource depots, placed by cosmic chance right on the doorstep of a planet we are determined to explore. Their most critical feature is their minuscule gravity. Landing a spacecraft on Phobos or Deimos requires only a gentle nudge, a whisper of thrust compared to the roaring engines needed to descend to Mars itself. This makes them the ideal gateway stations. Imagine a mission architecture where a crewed ship from Earth does not plunge directly to the Martian surface. Instead, it docks at an orbital station constructed on or around Phobos. Here, the crew can acclimate in a stable, low-gravity environment, using locally mined water to produce hydrogen and oxygen rocket fuel. From this secure perch, they then dispatch specialized landers for surface missions, which are now much smaller and simpler because they only need to fight Mars's gravity one way. When the surface crew is ready to return, they only need to ascend back to the Phobos station, not all the way back to Earth, making the entire endeavor far more efficient and reusable. This strategy transforms these tiny moons from curiosities into indispensable infrastructure. Their utility extends beyond logistics. The communication delay between Earth and Mars can be up to 20 minutes each way, making real-time control of complex robots on the surface frustratingly slow. But from Phobos, the delay to the Martian surface is less than 1 second. This opens the door to telepresence exploration at an incredible level of fidelity. An operator sitting in a control pod on Phobos could pilot a rover or a drone on Mars with virtually no lag, feeling the resistance in a robotic arm as it picks up a rock, or experiencing the panoramic view from a cliffside in real time. It would be the next best thing to being there, enabling detailed, delicate scientific work and complex construction projects long before a human boot ever touches the red dust. In this light, Phobos and Deimos cease to be mere moons. They are practice outposts, the most achievable first footholds beyond our Earth-Moon system. Mastering the technologies of deep space habitation, in situ resource mining, and long-term operations on these small bodies provides the essential proof of concept for every more ambitious outpost on our list. They are the training wheels for a multi-world civilization, offering a profound lesson that sometimes the smallest, most overlooked waypoints hold the keys to the grandest journeys. Saturn's rings may be its most famous feature, but its family of moons holds secrets that could rewrite the story of life's potential. Beyond the dramatic plumes of Enceladus and the methane haze of Triton, a quieter club of icy worlds may be hiding the same precious resource, liquid water, deep within their frozen frames. This is the Hidden Ocean Club, and its members like Dione, Rhea, and even the surprising Mimas suggest that buried seas might be the rule, not the exception, for mid-sized icy moons across the cosmos. Dione presents a world of stark, serene beauty. Its leading hemisphere is heavily cratered, a record of ancient impacts, while its trailing face is marked by a network of brilliant, wispy lines. These are not surface frost, but massive cliffs of bright ice, fractures in the crust where subsurface material has been exposed. For planetary scientists, these features are a clear signpost of a geologically active past. Something warmed Dione's interior long enough to cause its crust to crack and shift. While that internal heat may have faded, the legacy of that activity points to a tantalizing possibility. Data from the Cassini spacecraft suggests Dione, too, may possess a global ocean, a layer of liquid water sandwiched between its rocky core and its icy shell. This ocean would be far deeper than Enceladus's, perhaps 60 miles down, making it a silent, dark, and stable reservoir. An outpost here would be a listening station, using sensitive instruments placed on the surface to detect the subtle gravitational tug or magnetic signatures of that distant, buried sea. Then there is Rhea, Saturn's second largest moon. It appears as a dull, heavily cratered ball of ice, a seemingly ancient and quiet world. Yet Cassini's measurements revealed a mystery that still puzzles scientists. As the spacecraft flew by Re, it detected a faint and unexpected pattern in the Moon's own weak magnetic field. One compelling explanation for this signal is the presence of a global, salty ocean sloshing beneath the ice. The salt would make the water electrically conductive, and its movement through Saturn's magnetic field could generate the faint traces Cassini observed. If confirmed, this would be a revelation. Re lacks the intense tidal heating of Enceladus, so its ocean, if it exists, would be kept liquid by a different recipe, likely a mix of internal heat from radioactive decay and antifreeze compounds like ammonia. This expands the menu of possibilities for how these hidden oceans survive. A base on Re would be dedicated to solving this puzzle, drilling through the thick, ancient ice not just to reach water, but to understand the diverse ways a world can nurture a sea in the dark. The most shocking potential member of this club, however, is Mimas. Famous for its gigantic Herschel crater that gives it an uncanny resemblance to the Death Star from science fiction, Mimas seemed the least likely candidate for a subsurface ocean. It is small, heavily cratered, and shows no signs of the surface cracking or geysers seen on its siblings. But careful analysis of Cassini's images revealed a subtle wobble in the Moon's rotation, a libration that was larger than models predicted. That extra wobble suggests Mimas's interior is not uniform. One explanation is a hidden ocean, perhaps 20 to 30 kilometers beneath its scarred surface. Another possibility is a rugby ball-shaped rocky core. Either scenario means this small moon is far more complex inside than its battered exterior lets on. The idea that even Mimas could harbor a secret sea is what truly shifts the paradigm. It implies that when certain conditions of size, composition, and internal heat are met, a subsurface ocean might be a common outcome, a standard feature for a whole class of icy worlds. This realization transforms the challenge for future explorers. The question is no longer if we can find another ocean, but how we learn to see them. Our technology must evolve from mere observation to deep sensing, developing tools that can peer through miles of ice to map the contours of these alien seas, gauge their salinity, and listen for the echoes of their currents. The Hidden Ocean Club tells us that the solar system may be filled with these buried, liquid sanctuaries. Our task is to learn their language, to hear the quiet call of water in the deep freeze, and to one day devise the gentle, precise methods that might allow us to say hello. The search for new homes does not stop at the orbit of Neptune. Far beyond the last gas giant, in the deep freeze of the Kuiper belt, worlds of profound stillness hold their own secrets. Pluto, once the 9th planet, is now the king of this icy domain, and its largest companion, Charon, tells a story of cosmic intimacy. These two bodies are locked in a gravitational embrace so tight they forever face each other, a binary system dancing in the dark. Charon's surface is a stark landscape of water ice, but its most striking feature is a mysterious reddish stain at its north pole. This cap is made of complex organic molecules called tholins, created when methane from Pluto's thin atmosphere is zapped by sunlight and solar wind, eventually drifting down to coat Charon's frozen plains. These tholins are the building blocks of more complex chemistry, a frozen record of processes that could lead to life's ingredients elsewhere. More intriguingly, Charon shows signs of a fractured past. Long, deep canyons and tectonic scars suggest this moon was once warm enough inside for its water mantle to be liquid. This hints at a possible subsurface ocean in its youth, kept fluid by the heat of radioactive decay and the fierce tidal forces of its initial, chaotic formation with Pluto. While that ocean is likely frozen solid today, it would have left behind a legacy of stretched ice and reformed geology. For a future outpost, this ancient, deep frozen water ice is a priceless resource. It is a time capsule, water that has been locked away since the solar system's dawn, pure and untouched. A station on Charon could serve as a gateway to the entire Kuiper belt, processing this primordial ice into fuel and air, while studying the tholin-coated terrain to understand how organic chemistry unfolds in the coldest reaches of space. To truly grasp the scale of our potential neighborhood, we must look even farther to the scattered disk. Here, in a realm of staggering distance and perpetual twilight, orbits the dwarf planet Eris, slightly more massive than Pluto. And Eris has a moon, Dysnomia. This tiny companion, orbiting a world so distant it takes over 550 Earth years to circle the Sun once, represents the absolute frontier. Dysnomia is an example of an extreme trans-Neptunian object, a piece of primordial solar system material that has remained almost unchanged for 4.5 billion years. Its surface and that of Eris are likely coated in methane ice that has slowly sublimated and refrozen over eons, creating a landscape of almost supernatural purity. The resources here are not just water and rock, they are historical artifacts. The ices contain the pristine chemical signatures of the solar nebula from which our entire planetary system coalesced. Establishing any presence this far out would be a monumental feat of endurance, a testament to ambition itself. The sun is a merely bright star here, rendering solar panels useless. All power must come from nuclear sources. A signal from Earth would take over a day to arrive, meaning any outpost would need near total autonomy, making every critical decision on its own. To live and work at Dysnomia would be to operate at the very edge of human reach, using resources that have never felt the warmth of a close sun, in a silence so deep it is absolute. It would be less a colony and more a monument, a beacon showing we can learn from and survive within the oldest, coldest archives of our own cosmic origin story. This sprawling tour across 20 moons reveals a stunning diversity of possible homes, yet a crucial question remains: what does it truly mean for a moon to support a human outpost? The answer lies not in a simple yes or no, but in a practical framework, a resource matrix we can use to score each world. Think of it as a cosmic checklist for survival. 3 categories are non-negotiable: water, building materials, and a reliable source of energy. Water is the ultimate multitasker. Beyond drinking and growing food, its molecules can be split into breathable oxygen and hydrogen, the most powerful chemical rocket fuel known. Building materials mean the local soil and rock, or regolith, which can be processed into concrete or simply piled high over habitats to block cosmic radiation. Energy is the spark that makes everything else possible, whether it comes from distant sunlight, compact nuclear reactors, or a moon's own internal geothermal heat. Now, let's apply this lens. Europa scores phenomenally high on water, with a global subsurface ocean, but fails dramatically on radiation shielding and surface energy. Its sunlight is weak and its environment is bathed in Jupiter's lethal belts. At base there is a profound engineering challenge, requiring us to bring our own power and bury ourselves deep in ice for protection. Titan presents almost the opposite profile. Its thick atmosphere provides natural radiation shielding, a huge advantage, and its lakes of liquid methane and ethane are vast reservoirs for chemical energy and manufacturing. Yet accessible water ice is locked away in a deeply frozen crust, making it a resource that is present but difficult to harvest. Its energy score is mixed. Solar power is useless in the dim orange haze, but chemical and potential nuclear options are strong. Then consider Callisto. It doesn't have the obvious drama of a subsurface ocean or methane rain. Instead, it offers something foundational: strategic safety. Its position outside Jupiter's worst radiation belts and its abundant surface water ice give it high marks for both shielding and water access. It may lack the exotic chemical wealth of Titan or the confirmed ocean of Europa, but its overall balance makes it the most plausible site for a first permanent Jovian outpost, a stable platform from which to operate. This matrix shows us that support is a spectrum. A moon like Enceladus offers incredibly accessible water via its plumes, but virtually no building materials on its smooth, icy surface and requires imported energy. A moon like Ganymede offers strong magnetic shielding and immense water resources, but its substantial gravity makes landing and launch more costly. The final score for any moon depends entirely on our technology and our goals. Is the mission a short-term scientific outpost willing to bring most supplies from Earth, or is it a long-term, self-sustaining settlement that must live entirely off the land? The resource matrix transforms our list from a gallery of wonders into a strategic menu. It allows us to match our ambitions with a world's specific gifts, choosing the right tool for the job as we learn to build not just a single new home, but an entire interconnected civilization among the moons. The blueprint for survival shifts with every new gravity well and atmospheric pressure. On Enceladus, the most logical base might resemble a cryovolcano itself, a structure designed not to resist the environment, but to embrace its unique offering. Instead of drilling down, architects could position a station directly over one of the moon's famous tiger stripe fractures. Here, collectors shaped like giant inverted funnels would capture the constant snowfall of ice particles ejected from the subsurface ocean. This material, already in a fine, processed state, could be melted for immediate water, analyzed in on-site laboratories for scientific study, or electrolyzed into hydrogen and oxygen for fuel and air. The entire habitat would likely be buried beneath meters of that same ice for radiation shielding, creating a silent, subsurface research station living off a moon that willingly shares its secrets. Contrast this with the engineering required for Titan. Here, the thick atmosphere and liquid hydrocarbon seas invite a completely different approach, a floating outpost. Picture a broad, stabilized platform anchored on a methane lake like Kraken Mare. Its buoyancy would come not from air, but from the dense liquid itself. The station's exterior would be a marvel of cold, adaptive materials, designed to remain flexible and strong at temperatures that would shatter ordinary metals. Its most critical systems would focus on processing the environment, drawing in the nitrogen-rich atmosphere to create a breathable buffer for interior spaces, and siphoning methane from the sea to power generators or synthesize plastics for expansion. From such a platform, submersible drones could explore the dark depths below, while aerial vehicles, almost effortless in the thick air, could map the shorelines of an alien continent. For sheer dramatic setting, few locations rival the cliffs of Verona Rupes on Miranda. This staggering feature, possibly the tallest cliff in the solar system, plunges for kilometers. Building into its face offers a powerful advantage: natural shelter. A habitat complex anchored within the cliffside would have one wall formed by the ancient, primordial rock of the moon itself, providing immense protection from cosmic rays and micrometeorites. Access tunnels and viewing ports could be carved directly into the cliff, with elevators or cable systems connecting different levels of the base. The view from such a perch would be breathtaking, overlooking a chaotic valley floor that tells the story of the moon's violent reassembly, a constant reminder of the powerful forces that shape these small worlds. Meanwhile, at Mars, the challenge of Phobos is its negligible gravity, which is debilitating for human health over the long term. The solution might be a rotating habitat, a large, circular station built on or orbiting the moon. By spinning this ring, engineers could create artificial gravity along its inner rim, allowing residents to live and work with their bodies functioning normally. This station would serve as the vital command and logistics hub, its rotation simulating Earth-like conditions while its location provides that crucial 1-second link to the Martian surface for telepresence operations. All these visions share one non-negotiable principle: living off the land, a practice called in situ resource utilization. This is the art of turning alien dirt and air into a home. On the Moon or Mars, this means using regolith, the local soil, as the primary building block. Massive 3D printers could sinter this material layer by layer into sturdy walls, radiation shields, and even landing pads, using only the power of focused sunlight or microwaves. The most universal process, however, is water splitting. Wherever water ice is found, from the poles of Mars to the plains of Callisto, electrolysis units will hum, using electricity to crack H2O into life-saving oxygen and versatile hydrogen fuel. Titan adds another layer: atmospheric processing. Its dense nitrogen air can be filtered and compressed to fill habitats, while the methane can be refined. These are not just survival tricks, they are the foundational technologies for a self-sustaining presence. Each outpost, therefore, becomes more than a shelter. It is an integrated system, a growing ecosystem where the waste from one process becomes the input for another, all tailored to the specific, alien rhythm of its host moon. The architecture is the embodiment of our adaptability, a physical declaration that we can learn to thrive in places that follow rules written for geology, not for life. The most advanced life support system ever built is the human mind, and it was never designed for a sky without a moon or a horizon without end. On a world like Callisto, the sun is a bright star, but the dominant feature in the sky is Jupiter, a striped giant that never sets, a permanent, looming presence that defies our earthly sense of day and night. Inside a habitat, artificial cycles of light will try to mimic the 24-hour rhythm our biology expects, but outside the viewport, the universe is a static painting. This sensory deprivation, the lack of weather, of seasons, of the color green, can erode mental well-being in subtle, profound ways. Astronauts on the International Space Station speak of the overview effect, a sense of unity and awe from seeing Earth as a fragile blue marble. For a permanent resident of a distant moon, that marble shrinks to a pale blue dot and then vanishes from the sky entirely. The psychological architecture of an outpost must be as carefully engineered as its airlocks. Virtual reality windows streaming forests and oceans, communal spaces designed for both privacy and connection, and meaningful work that ties each individual to the larger mission are not luxuries, they are critical infrastructure for the soul. Our bodies face an equally radical adaptation. The gravity on these moons is a fraction of Earth's. On Titan, you would weigh about as much as you do on our own moon, able to take bounding leaps. On Ceres, you could be light enough to launch yourself into a low orbit with a strong jump. This sounds like fun, but it is a slow crisis for human physiology. In low gravity, bones lose density, muscles atrophy, and the cardiovascular system grows lazy without the constant work of fighting Earth's pull. The solution is relentless artificial effort. Every outpost will need a gym, but not like any on Earth. It will be a room of specialized torture devices, with treadmills that use harnesses to simulate weight, resistance machines that maintain muscle mass, and vibration plates that hopefully trick bones into staying strong. Exercise ceases to be optional recreation and becomes a mandatory, daily prescription for survival, a 2-hour chore to prevent your own body from decaying. These physical and mental strains converge in the social sphere. An outpost crew is a sealed micro-society, a family you cannot leave. Conflicts that might be trivial on Earth, a disagreement over noise or a habit of leaving tools out, can fester and magnify under the pressure of perpetual confinement and shared danger. Mission planners will select for psychological compatibility and train crews in conflict resolution for years, but they cannot predict everything. How does a society of a few hundred, separated from Earth by a communications delay of hours or even days, govern itself? Earth-based command cannot mediate a real-time dispute. The community must develop its own norms, its own justice, and its own ways to celebrate and mourn. Over decades, these isolated groups will inevitably begin to diverge culturally from Earth. Their language might incorporate new slang for local phenomena. Their art and stories will reflect the stark beauty of their new home, the ever-present Jupiter or the amber haze of Titan. They will develop a unique identity, a pride of place, seeing themselves not as exiled Earthlings but as Callistans or Titanians. This raises a profound, long-term question about the very purpose of these settlements. Are they mere extensions of Earth, outposts reporting back to a home that still defines their culture and laws? Or do they become something new entirely, seeds of independent human branches evolving under alien suns? The answer will determine the social technology we send with them. Do we provide rigid protocols for every scenario, or do we equip them with flexible ethical frameworks and tools for self-determination? The ultimate test of a multi-moon civilization may not be whether we can build a dome on Europa, but whether we can build a society there that remains human and yet becomes something more. These isolated societies would not remain alone for long. The very specialization that defines them creates a powerful, inevitable pull toward connection. Titan's factories produce polymers and fuels, while Europa's research labs generate priceless data on its hidden ocean. Callisto's shipyards need metals, and the crews on the Martian moons crave fresh food from Ceres' orbital greenhouses. This is the birth of an intermoon economy, a slow but vital network of trade that transforms a collection of outposts into a true, interdependent civilization. The foundation of this economy is simple comparative advantage. No single world has everything it needs to be completely self-sufficient, but each possesses something in extraordinary abundance. Titan's atmosphere is a hydrocarbon refinery, offering methane and ethane that can be processed into rocket fuel, plastics, and synthetic materials. Imagine bulk freighters, their hulls coated in dark polymers made on Titan itself, departing with tanks full of liquid methane, destined for the fuel depots orbiting Mars or Jupiter. In return, they might carry advanced electronics manufactured in the microgravity of Phobos, or specialized medical supplies from Earth that are too complex to produce locally. Europa's contribution would be one of purity and profound scientific value. Its subsurface ocean, once accessed, could provide vast quantities of the cleanest water in the solar system, ideal for life support and electrolysis into oxygen and hydrogen. More significantly, if any biological signatures or unique organic compounds are discovered in its depths, carefully curated and sterilized samples could become the most valuable scientific commodity ever traded, shipped in heavily shielded containers to research centers across the system. Europa would export knowledge in its most literal and precious form. The transportation hubs of this network are already clear. The Martian moons, Phobos and Deimos, with their negligible gravity, are perfect ports. Ships coming from the inner solar system can dock here without fighting Mars gravity well, transferring cargo and passengers to dedicated Martian landers. These moons become bustling interplanetary terminals, where goods from Ceres' mineral-rich belt meet shipments from the outer moons, all being sorted and redirected. Ceres itself, the largest object in the asteroid belt, acts as a central warehouse. Its mixture of water ice and silicate rock makes it a prime source of raw materials for construction and radiation shielding, materials that can be launched off its small gravity well with relative ease to supply building projects everywhere. Making this slow-motion commerce physically possible demands a revolution in propulsion. Chemical rockets, the workhorses for getting off Earth, are far too thirsty for these decade-long hauls. The freighters of the intermoon economy would rely on engines that trade raw power for incredible efficiency. Ion drives, which use electricity to accelerate charged particles to extreme speeds, provide a gentle but continuous thrust for years on end, perfect for moving high-value, low-mass cargo like data drives or medical samples. For bulkier goods like tanks of water or metallic asteroids, nuclear thermal rockets become the likely solution. These engines use a fission reactor to superheat a propellant like hydrogen, offering a much more powerful and efficient push than chemical engines, cutting transit times between Jupiter and Saturn from decades to perhaps a single decade. This perspective changes everything. It frames solar system colonization not as a series of flags planted in lonely soil, but as the weaving of a collaborative web. No outpost is an island, each is a vital node in a larger human project. The water miner on Ceres, the chemist on Titan, the biologist on Europa, and the pilot navigating the freight routes between them are all part of the same grand endeavor. Their survival and prosperity become intertwined. A disruption in the methane supply chain from Titan could stall construction at Callisto. A breakthrough in radiation shielding at Ganymede could make the Uranian frontier suddenly accessible. This interdependence fosters a new identity, a solar system-wide citizenship where the success of a distant community is celebrated as a victory for all. The economy becomes more than an exchange of resources. It is the circulatory system of a new kind of human society, one distributed across the cosmic archipelago, finally at home among the moons. A thriving economy among the moons creates a new kind of frontier, one without a sheriff or a shared rulebook. The legal framework that governs human activity in space today was written in 1967, a document born of the Cold War called the Outer Space Treaty. Its core principles are noble and clear. Space is the province of all humankind. No nation can claim sovereignty over a celestial body, and activities must be conducted for peaceful purposes. But this treaty was drafted before anyone seriously contemplated mining an asteroid or founding a city on an ice moon. It speaks in grand, aspirational language, but offers little practical guidance for the gritty reality of drilling for water ice or harvesting atmospheric methane. The treaty declares that the exploration and use of space shall be carried out for the benefit and in the interests of all countries. Yet it does not define how a private company that invests trillions to extract resources from Titan must share those benefits with the rest of humanity. This legal vacuum is the next great wilderness we must navigate. The most immediate ethical dilemma waits in the dark waters of Europa. Current planetary protection protocols designed to prevent contamination treat Europa as a potential sanctuary for life. They mandate that any spacecraft contacting its surface or ocean must be sterilized to an extreme degree. But what happens when the mission shifts from a flyby probe to a permanent human outpost? The very act of drilling through the ice shell, even with the most careful technology, risks introducing Earth microbes into that pristine environment. And if we discover native life forms, even simple microbes, our presence becomes an existential question for them. Do we have the right to alter or potentially extinguish a separate genesis of life for our own gain? The answer will force us to choose between two profound human impulses: the drive to explore and expand, and the responsibility to preserve and protect. This is not a scientific question, but a philosophical one that will define our character as a spacefaring species. On a world like Titan, the questions are social. A self-sustaining settlement will, over generations, develop its own customs, values, and perhaps even its own interpretation of laws sent from a distant Earth. Who has the authority to govern daily life in a habitat floating on a methane sea? Is it a corporate charter from an Earth-based company that funded the colony? Is it an extension of the legal system of the nation that launched the original mission? Or does the community itself, through a council of elders or a digital democracy, forge its own social contract? These settlers will face unique moral challenges with no earthly precedent. How do they allocate limited life support resources in a crisis? What rights and protections does an artificial intelligence integral to the colony's function possess? The cultural guidelines for Titan will be written in real time under immense pressure, creating a new branch of human culture adapted to an amber sky. This ambiguity over law and ethics sows the seeds for potential conflict. While the Outer Space Treaty forbids national appropriation, it says nothing about two private entities claiming the same resource-rich crater on Ceres. The most valuable real estate in the solar system, like the geyser sites on Enceladus or the water ice deposits at the lunar poles, are finite. Without clear, agreed-upon rules for staking and developing a claim, disputes are inevitable. Will there be a solar system court to adjudicate these conflicts, or will we see a new form of frontier rivalry, played out with drones and digital blockades instead of six-shooters? Establishing a transparent and fair system for resource rights is not just an administrative task, it is a prerequisite for peaceful expansion. It is the difference between building a collaborative archipelago and triggering a new scramble for territory that echoes the darkest chapters of our terrestrial history. Ultimately, these outposts hold up a mirror to our deepest principles. They force us to decide what values we will pack for this infinite journey. Is our expansion driven solely by resource extraction and strategic advantage, or will we embed ideals of stewardship, cooperation, and the preservation of wonder into the very foundations of our new homes? The laws we draft and the ethical lines we draw now will echo for centuries, determining whether the story of humanity among the moons is one of enlightened community or of repeated terrestrial mistakes cast onto a grander, darker stage. The final frontier is not just a place, it is a test of our collective wisdom. The legal questions we leave unanswered today will shape the physical reality our grandchildren inherit tomorrow. So when does this future begin? Not as science fiction, but as a schedule we might live to see. The journey from robotic scout to bustling outpost unfolds in distinct, overlapping phases, a century-long project that fits within a conceivable human lifespan. Phase 1 is already underway, the age of the robotic pioneers. Throughout the 2030s and 2040s, a fleet of specialized scouts will fan out across the solar system, each tasked with answering a single, critical question. The Europa Clipper will meticulously map the icy shell of Jupiter's ocean moon, searching for the thinnest spots and potential plume deposits. At Saturn, the Dragonfly rotorcraft will touch down on Titan, flying from site to site across its organic dunes to sample the chemistry of an alien prebiotic world. Parallel missions will target the Martian moons, drilling into Phobos to confirm water ice reserves, and orbiters will continue to scrutinize Ceres for signs of subsurface brines. Their primary goal is not just discovery but risk reduction. They are prospectors creating detailed resource maps and identifying the safest, most valuable plots of celestial real estate for the settlers who will follow. Their final, most complex act may be sample return, a technological marvel where a spacecraft grabs a cup of material from a distant moon and fires it back on a precise trajectory to Earth, allowing scientists in terrestrial labs to hold a piece of another world and finally know what we are truly building with. Phase 2, beginning perhaps in the 2050s, marks humanity's first tentative steps into this new archipelago. These are not permanent colonies, but extended camping trips at the edge of our reach. The most likely destinations are the stepping stones, the Martian moons of Phobos and Deimos, or the dwarf planet Ceres in the asteroid belt. A crewed mission would likely orbit or land on one of these small bodies, establishing a temporary habitat for a year-long stay. Their mission is hands-on testing. They will operate the first pilot-scale mining equipment, turning local regolith into a test batch of radiation-shielding bricks. They will practice running a closed-loop life support system for months on end, recycling every drop of water without a resupply from Earth. Most importantly, they will live the reality of deep space psychology, learning how a small team functions when the blue marble of home is just a distant star in the black. These missions are the essential dress rehearsals, proving the core technologies of in-situ resource utilization and long-duration survival far from Earth, building the confidence needed to commit to a permanent presence. Phase 3, targeting the 2080s, is where the dream solidifies into a foundation. With lessons learned from the stepping stones, we establish the first permanent outposts on the most strategically viable worlds. Callisto, with its relative safety and abundant surface ice, is a prime candidate for a fortified Jovian research hub. Triton, with its atmospheric shielding and chemical wealth, could see the first floating station on its methane seas. These are not temporary camps, but rotating habitats designed for continuous occupation. The first crews might serve tours of 2 to 3 years, but the lights in the habitat never go off. As one crew departs, another arrives, creating an unbroken human presence. These bases will evolve from pure science stations into something more, incorporating small-scale manufacturing, local food production in pressurized greenhouses, and the first elements of infrastructure, like landing pads and fuel depots built from local materials. They become the first true footholds, the initial nodes in the growing network, places where children might be born under an alien sky, forever changing the meaning of the word home. Phase 4 stretches across the entire 22nd century and beyond, defined not by arrival but by connection and independence. This is the era of the intermoon economy coming to life. With multiple permanent outposts established, the focus shifts to linking them together. Freighters running on efficient nuclear thermal or ion drives begin their slow, regular routes between Titan's fuel refineries, Ceres' mineral deposits, and the water-ice markets of the outer moon. The outposts themselves graduate from mere footholds to self-sustaining settlements. They develop their own specialized industries, export their unique products, and cultivate cultural identities distinct from Earth. The ultimate milestone of this phase is true self-sufficiency, a point where a settlement can maintain and grow its population and technology without any critical imports from the home planet. This does not mean isolation, but rather a mature interdependence within the solar system community. It is the moment the archipelago becomes a civilization, a distributed human presence capable of enduring even if the link to Earth were severed, securing the future of our species across more worlds than one. This timeline is not a promise but a plausible map, a series of logical next steps built on the probes we are launching now. It means the first person to take a permanent breath on Callisto may already be alive today. The blueprints and timelines are not merely engineering exercises, they are the scaffolding for a profound human transformation. This endeavor, the establishment of a network across 20 moons, transcends the practical. It is, at its core, an existential insurance policy written across the solar system. By distributing our presence, we safeguard the collective future of human thought, art, and discovery against a single point of failure. A catastrophic event on Earth, whether natural or of our own making, would no longer mean the end of the human story. Our narrative would continue from a habitat on Callisto, a station on Titan, ensuring that the light of consciousness, in all its fragile complexity, endures. This is the ultimate argument for becoming a multi-world species, not as an escape from Earth, but as a commitment to its legacy, preserving the chance for tomorrow no matter what happens today. The scientific payoff is equally monumental, offering a comparative laboratory on a scale we can barely comprehend. Imagine studying not one, but several subsurface oceans, each with its own unique chemistry, heat source, and history. We could compare the potential biology of Europa's dark sea with the ancient, deep ocean of Ganymede or the accessible Plumes of Enceladus. This isn't about finding a single answer to the question of life. It's about discovering the many different rules life might follow, rewriting biology from first principles. We would gain front-row seats to exotic chemistries in action, from the hydrocarbon cycles of Triton to the cryovolcanic processes sculpting distant moons. Each outpost becomes a new vantage point, a fresh pair of eyes through which to observe the history of our solar system, piecing together a story more intricate and wondrous than any we've yet imagined. Beyond survival and science lies something equally vital, the fulfillment of a fundamental human drive. For millennia, we have looked to the horizon and wondered what lies beyond the mountains, across the oceans, in the depths of space. This restless curiosity is not a frivolous distraction. It is woven into our nature. To cease exploring, to turn inward and accept a single planetary cradle as our permanent boundary, would be to deny a core part of who we are. The expansion into the cosmic archipelago promises a cultural and intellectual renaissance unlike any in history. New environments will inspire new forms of art, music, and literature born from the stark beauty of an eternal Jovian sunset or the gentle fall of methane rain. New social structures tested in isolation may offer innovative solutions to ancient challenges of community and governance. The very experience of living under different skies will expand the human perspective in ways we cannot yet predict, enriching our collective understanding of what it means to be alive, to be a society, to be human. This journey, therefore, is about more than building habitats. It is about building possibilities. It is an investment in a future where human experience is no longer defined by a single world, but illuminated by many. The ultimate payoff is the vast, uncharted territory of knowledge, culture, and identity that awaits us when we step off our planetary porch and learn to make a home among the quiet, waiting moons. Our current map of the cosmic archipelago is still drawn in faint lines. Beyond the 20 major moons we have charted, each giant planet is encircled by a cloud of silent, tiny companions, often just a few miles across. These are the irregular moons, captured asteroids or fragments from ancient collisions, tumbling in distant, looping orbits. To our current telescopes, they are little more than faint points of light. Yet within their small, dark frames could lie resources or strategic positions we have not yet dreamed of. Imagine a captured metallic asteroid, rich in platinum group metals, now orbiting Saturn as a moon. Or a carbonaceous body, a frozen lump of primordial organic material circling Uranus. Their small size makes them gravity wells, allowing for easy landing and departure, perfect for automated mining stations that feed processed materials into the wider intermoon economy. Their very obscurity might be their greatest asset, offering stable, predictable orbits far from the complex gravitational dances of the larger moons, ideal for placing communication relays or navigation beacons that guide ships across the outer darkness. The true number of potential outposts is not fixed at 20. It is a number waiting to be rewritten by the next generation of eyes we turn to the sky. Instruments like the Vera C. Rubin Observatory with its relentless all-sky survey will discover thousands more of these faint objects, cataloging their paths and hinting at their compositions. Even more powerful space-based telescopes, peering in infrared and optical wavelengths, will analyze the faint sunlight reflected from their surfaces, telling us if they are made of dark carbon, bright ice, or valuable metal. Each new discovery adds another potential node to our future network, another specialized waypoint in the grand architecture of a solar system civilization. This is the profound lesson of our journey. The list we have explored is not a final destination, but a first draft. It is a testament to how much we have learned and a humbling reminder of how much we have yet to see. The cosmic archipelago is larger and richer than we can currently perceive. Our future among the moons will be built not only on the worlds we know today, but on the hidden gems we have yet to find, each one waiting in the silent dark to reveal its purpose. So where does this leave us on the map of tomorrow? With 20 candidates and a century of work ahead, we need a practical guide, a ranking based not just on wonder, but on a balance of what we can reach, what we can use, and what we must learn. Think of it as a strategic tier list for our cosmic archipelago, a way to organize our ambitions from the nearest shores to the farthest frontiers. The first tier is our training ground, the worlds we can realistically touch within the next few decades. This is Tier 1, the stepping stones. It includes the Martian moons, Phobos and Deimos, and the dwarf planet Ceres in the asteroid belt. Their paramount advantage is accessibility. They are the closest and most forgiving targets beyond our own moon, with minimal gravity making landing and departure relatively simple. Phobos offers that crucial 1-second telepresence link to the Martian surface, turning it into an orbital command center. Ceres, with its suspected subsurface brines and mixture of water, ice, and rock, acts as a prototype for an off-Earth resource depot. Establishing a continuous human presence here is not a far-flung dream. It is the logical next major step after the lunar gateway, a place to perfect the technologies of living off the land before we venture into the deeper dark. Tier 2 contains the crown jewels of scientific discovery, worlds of staggering promise that come with equally staggering challenges. Europa, Enceladus, and Triton are the high-priority, high-difficulty targets. Their scientific value is unparalleled, a subsurface ocean that may host life, geysers offering free samples of that ocean, and a complex probiotic chemical factory under a thick atmosphere. Yet the barriers to a human outpost are immense. Europa bathes in lethal radiation, requiring habitats buried under miles of ice. Enceladus has virtually no gravity and offers little surface material for construction. Triton is drowning in profound cold and lacks easily accessible water. These are not places for early settlements. They are destinations for robotic avatars and, eventually, heavily protected scientific citadels where the primary mission is profound discovery, not expansion. Our third tier shifts focus from pure science to strategic support. These are the future hubs, the ports and fortresses that enable operations across a planetary system. Callisto, with its relative safety from radiation and abundant surface ice, is the prime candidate for the first permanent Jovian outpost, a fortified base to teleoperate on Europa and Ganymede. Ganymede itself, with its protective magnetic field and immense resources, could evolve into a central capital for the Jupiter system. Far out at Neptune, Triton stands as the ultimate gateway to the Kuiper belt, a captured primordial world rich in volatile ices that could fuel the final outward push. These worlds may not have the immediate biological allure of Tier 2, but they offer the stable platforms, the resource wealth, and the strategic locations needed to sustain a permanent civilization across the outer solar system. Finally, Tier 4 encompasses the longer-term prospects, the remaining major moons of Uranus and Saturn, along with distant companions like Charon. These are the specialized waypoints and the deep time archives. A base on the fractured cliffs of Miranda could mine minerals brought up from a catastrophic past. An observatory on the dark plains of Umbriel would study the cosmos through perfectly clear, still air. Each holds unique resources and scientific questions, but their extreme distance or specialized nature places them on the roadmap for a mature, already thriving inter-moon economy. They represent the filling in of the map, the expansion of a network that is already secure and self-sustaining. This tiered view is not a rigid schedule, but a fluid strategic overlay. It acknowledges that our journey will be one of parallel paths. While we are building our first permanent habitat on a Tier 1 world like Ceres, our robotic proxies will be doing the dangerous preliminary work on the Tier 2 wonders like Europa. And as we learn to survive in the outer system from a Tier 3 hub like Callisto, we will be preparing the technologies needed to finally endure in the Tier 4 frontiers. The roadmap is not a single line but a spreading web, each connection strengthening the whole. It tells us that the future is not a single destination but a growing neighborhood, built one achievable step at a time, until the quiet moons no longer seem like distant outposts but familiar lights in our home sky. This grand tapestry of moons paints a future not of a single new Earth, but of a connected, resilient civilization. It is a vision that moves us from a species confined to one fragile rock to a civilization distributed across an entire system, where the failure of any one home does not end the human story. The journey will be our greatest teacher. Each challenge, from shielding against Jovian radiation to synthesizing air from Titan's haze, will force innovations that ripple back to benefit life on our first home. The very act of learning to live in these alien environments will deepen our understanding of biology, climate, and sustainability in ways we cannot yet foresee. This is not an escape from Earth but an extension of its potential. Our night sky will transform from a backdrop of distant stars into a map of neighborhoods. Jupiter will be known not just as a gas giant, but as the anchor for the Callisto shipyards and the Europa research preserves. Saturn will be the domain of the Titan polymer factories and the Enceladus science stations. These are not mere points of light, but places with weather, resources, and communities. They become part of our human geography, expanding the concept of home to a truly cosmic scale. The path forward is clear, a series of logical, courageous steps. It begins with the robotic prospectors already in development, continues with the first extended cruise on the stepping stones of the asteroid belt, and culminates in the bustling, interconnected network of specialized outposts. This endeavor calls for more than engineers and astronauts. It needs artists, ethicists, architects, and storytellers to help shape the culture of these new worlds. It is a project that can unite our global civilization around a common, uplifting goal, turning our gaze outward in a spirit of shared discovery. The cosmic archipelago is no longer science fiction. It is a strategic, achievable, and necessary horizon for humanity. The 20 moons we have explored are the first candidates, the most obvious harbors in a vast and waiting ocean. They offer us a future of endless discovery, profound resilience, and a legacy written not just on Earth, but across the silent, waiting expanse of our solar system. The next chapter begins with the choices we make today. If this vision of our future excites you, subscribe for more deep dives into humanity's next steps, and let us know in the comments which moon outpost you would want to visit first.